these types of problems. I've given you a general kind of template for how you can do that, right? You first identify what two units you're converting between, then you determine a pathway to get from one unit to the other, and then you just go through and make sure the units are canceling out, right? So that gives you a general way to approach these problems. However, in practice, it's a little bit more challenging than that, right? Because sometimes developing that pathway isn't exactly the easiest thing to do. So one of the things we talked about is using those flowcharts, right? You have your note card that you can have on your exam. Maybe write down those flowcharts to know how to convert between different things. All right, so if you can use a flowchart and you use it on the exam, it'll make those things go a lot faster. Okay. All right, so last time we started talking about, well, before we started talking about solutions, we got into finishing up percent and percent yield calculations, right? So we were talking about percent yield, and what was the percent yield equal to? Right, how do we define the percent yield of a reaction? Yep, actual yield over our theoretical yield times 100, right? That just gives us the percentage there. And where do we get the actual yield from? Yeah, we measure this, right? This is something that we're measuring or something that's given to us in a problem, right? Because, you know, if you're given a question on an exam, you don't necessarily have something to measure right in front of you. And the theoretical yield, where do we get that from? Yeah, this is from the balanced, right? Balanced chemical equation and the starting amounts. Right? So this is when we mix together non-stoichiometric amounts of each reactant. And what does it mean when I say non-stoichiometric amount of each reactant? Does anyone remember? It's sophisticated language, but it... So we're not mixing things according to the balanced chemical equation, right? Because usually when we mix things together, we weigh stuff out and mix them together. We have different concentration solutions and we mix them together. If we have a chemical reaction that has one mole of one reactant for every 2 moles of the other reactant, that means you need a number ratio of 1 to 2. When we measure out masses, we're not looking at number ratios, right? Because different elements and compounds weigh different amounts. So if we measure just 2 masses and mix them together, that means it's most likely, unless you measured it to the exact amount that you needed to match the moles, it's most likely going to be a non-stoichiometric amount of things that you mix together. And so to determine what the theoretical yield is, you have to then determine how much product you're going to make if you mix these 2 things together. And so you can be given problems where you have to determine that, or determine what the limiting reactant is, or you can be given problems where it's already assumed what the limiting reactant is, right? So this is from the balanced chemical equation and the starting amounts of each reactant. And then you have to determine what is theoretically the most product you can make from that reactant, right? So this is theoretically the theoretical max amount of product, right? Because if the chemical equation is 100% efficient, then you know for every one time the reaction happens, you will make exactly the amount of product molecules that are in the balanced chemical equation. In reality, though, you lose some reactant to side reactions. Sometimes not all of the reactants will get reacted. So in reality, you don't have something that's 100% efficient. So that's why we get the percent yield, right? We're never going to actually make 100% of what we start with. And so the theoretical yield was related to, so this is just a reminder, limiting reactant problems, which was the time before last, and also related to mass to mass calculations, right? So mass to mass calculations or any variation of that, right? So on the quiz last Monday, you were given a chemical reaction. You didn't have to go mass to mass calculations because you were given the moles of one of the reactants. So you did moles to mass, which is less steps. All any questions on percent yield, or does anyone have any questions from that or those lectures that they want to clear up? Well, okay. After that, we started talking about solutions and concentrations, right? So we had solutions, and solutions were comprised of two parts. What were the two parts of a solution? Solute and the solvent, right? Solute and solvent. And so what was the solute in a solution? Yep, this is what's being dissolved. And the solvent was what's doing the dissolving, right? What's doing the dissolving? Right, and so this is usually taking our solute that's in the solid phase and putting it in what we call the aqueous phase, right? So solvent molecules trap our solute molecules and allow them to float around in solution. That's why things dissolve in solvents, right? So sugar in water, you have water molecules that trap the sugar molecules and they float around with the water molecules. All right, and then we started talking about, well, solutions, we want to define the amount of whatever our solute is in that solution, and we do that using something called concentrations. And this tells us the amount of solute in a given amount of solution. And one thing to note is that solutions don't necessarily have to be liquids. Solutions can be mixtures of anything, right? These are just mixtures of, they can be mixtures of any phase of matter. So you can have gas solutions, you can have gas and liquid solutions, solid in liquid solutions, and so on. And so does anyone remember some of the units for concentration that we used, or that we defined? Molarity, that was a big one, right? Molarity is the most important unit of concentration for chemistry, right? This is what we use the most. Molarity, and does anyone remember what the definition of molarity was? Yep, it's the number of moles per liter of solution, right? So the amount of solute in units of moles, right? So if I gave you a certain amount of solute you dissolved in solution, I gave you the grams you dissolved in solution, how would you get the moles? Right, if I gave you the grams for any random solid. How do you go between grams and moles? What kind of quantity is a gram? Is it a unit of length, mass, time? Mass, right? So how do you go between units of mass and moles? Molar mass, right? They sound the same to each other, right? So this you get from converting the grams that you dissolve in a solution into moles divided by the volume of that solution, right? That's how you get units of molarity. And this was, I'll highlight it because this is the important one and what we'll be looking at for most of the concentrations going forward. In some of the other disciplines like health sciences and stuff, you may see some other concentrations. And those ones were going to be mass to volume percent, right? That one is a big one in the health sciences, right? That means what mass of solute do you have in a given volume of solution in the percentage-wise, right? So 2.5 grams per 100 milliliters would give you a 2.5% mass to volume. And we'll go over problems on how to do all this in a second. And then there was volume to volume percent, volume of solute and volume of solution. And then there was also mass to mass percent. All these have their uses, but again, the molarity is the most important for chemistry. All right, so these were the definitions of the different concentrations that we used. Really, The concentration, or the unit of concentration, just tells us how much of something we have per given solution, right? So how much solute is in an amount of solvent. And usually that's measured in some sort of amount in mass or moles per volume of solution. All right, any questions on any of those definitions before we start working on some of the problems? All right, so let's do this one together, and then I'll give you guys, let's see, do I want to do that one, or do I want to go? All right, so here we have a mass to volume percent of a solution prepared by dissolving 5 grams of potassium iodide, right? We know how to name that because we know how to name ionic compounds, to give a final volume of 250 milliliters, right? So we're given a couple of different values, and we want to solve for something, right? So what do we want to solve for here? We want to solve for what? We want the mass percent to volume rate, concentration of the solution, right? So we want to find the mass to volume percent of solution. So sometimes you'll see it written like that. Sometimes you'll see it written like the percentage first. This is what that means. And how this is defined is the amount of solution, or the amount of solute in mass, amount solute in mass. And give me an example of something in a unit of mass? Grams, right? So we'll use grams to define mass to volume per 100 milliliters of solution, right? And again, we have to be careful when we look at the solution because that's the volume of the total solution, which could be, if we're mixing 2 liquids together, the volume of solute and the volume of solvent. Right, those 2 things added together give us the total volume of the solution. In this case, though, we're dissolving a solid, right? Solids don't change the volume. If you add sugar to coffee, right, it doesn't change the volume of your coffee. You're not necessarily filling it up because it doesn't take up very much volume when it gets dissolved. So this is kind of the definition of what mass to volume percent is. How we go about working through a problem like this, where you're given the amount in grams and you're given the final volume of the solution, is we take the mass of solute. So what's our solute in this problem? Potassium iodide, right? Potassium iodide. So this is Ki in this case, divided by our volume of solution. What's our volume of solution? 250 milliliters, right? So this will be 5.0 grams divided by 250 milliliters. And this gives us the percentage in a decimal form of the mass per unit volume in the solution. So if you do this, you get 1 over 50. So this will be like 0.02. And we take that and we multiply it by 100%, and that'll give us 2% mass to volume for the solution. Make sure I didn't. What's 1 divided by 50? 1 divided by 50. Okay, yeah, 0.02. So when we're given the mass and we're given the final volume, all we do is we just take those 2 values, we divide it because that gives us the number of grams per milliliter, and we multiply it by 100 to give us a percent value for that. All right, so there's 2 different ways that you're going to be given these mass to volume percentages. One is going to be when you're given the amount of solute in grams and the amount of solution in volume. And then the other way the problem will be given to you is when you're given the concentration, it has to find out what's the volume or what's the amount of solute dissolved in that solution. All right, so this is all the answer would be. This would be a 2% mass to volume. And if we think about this, this is just a percentage way of saying what percentage of the solution, has, or what is the percentage of mass to volume in the solution, right? In this case, the mass is in units of grams. In general, when we're looking at mass to volume, it'll be grams per milliliter. Yep. And so that's because in general, if the numerator there is equal to that first ratio, and so you multiply it by 100 to give the concentration, or the concentration units that we're looking for, it becomes more clear when we're given the concentration and we're asked to find the amount that's in solution. And it's because so this should be, this will be, I'll correct this a little bit. This is gonna be the concentration, or the percentage of mass to volume of solution gives us our mass to volume percent concentration. Mass to concentration equals our percentage of mass to volume in solution. So the percentage of mass to volume in solution is just the ratio of the amount of mass given per milliliter, right? The way mass percent is defined is it's the amount per 100 milliliters. Right, so we know based off of, and it's because 100 milliliters gives us the percent value is why it's defined that way. So I know it's a little confusing. This tells us, the fraction of grams per milliliter, right? The units for this are grams per milliliter. That tells us the percent in decimal form of the mass to the volume in solution. Our concentration is defined as the percent mass to volume of solution divided by 100 milliliters of the solution itself, or per 100 milliliters of the solution. So when you get the decimal point, you multiply that by 100 to get a percentage value. And multiplying it by 100 is the same way as defining it as the concentration per 100 milliliters of solution. So I know it's confusing because the units, they don't work out exactly how you would expect based off of these percentages, right? Because we're dealing with percentages technically don't have units, but we're defining this concentration in percentage mass to volume for a given 100 milliliter solution. In practice, so I wouldn't think too hard about what these definitions mean, more about how we treat them in practice. So if we look at, for example, another question here where we're given a mass to volume percent of a specific drug, and we have a given volume of solution, then that's where this definition comes into play, right? Because 1.0 mass to volume solution is the same thing as 1.0 gram of solute per 100 milliliters of solution. So this is the value of our concentration. And this is important because it highlights an important way we can get the amount of solute for any units of concentration that we're dealing with, right? If we have a given concentration, and this problem is asking how much is in 65 milliliters of solution. So we're given the concentration, and we're given the volume. We want to find how many grams are actually in 65 milliliters of solution. Right. What would we multiply this value of concentration? So this is where per 100 milliliters comes in, because this is defined as 1 gram per 100 milliliters is how we write the units for a percent to volume solution. So what would we multiply that by to get just units of grams? Because we just want units of grams in the end. Inverse of what? Right, so if we're starting from, right, we're starting from concentration, and we want to go to grams of solute. In this case, the solute is clindamycin. Okay? Yeah, you want to cancel out the units of volume, right? Yep, so if we have 1.0 gram per 100 milliliters, we can multiply that by a volume, which in this case we're given the volume of the solution that we're looking at, right? And that'll cancel out the units of milliliters, and all we'll be left with is the units of grams, right? So 65, if we did this, this would be 0.65 grams of clindamycin. And if we notice that for any of our concentrations, especially anything that deals with volumes, if we're looking for a certain amount of solute for a given solution, we take the value of the concentration and multiply it by the volume of the solution. All right, so in general, the value of the concentration times a volume equals an amount. And that amount, depending on the concentration, can either be units of grams or moles. All right, so for molarity, if you multiply it by a volume, you get units of moles. For mass to volume percent, you get units of grams. You say, well, how is this useful? Why is this unit of concentration useful at all? Well, if you're trying to give a specific dosage to a patient, a lot of time those dosages are given in grams per kilogram of body weight, for example, right? So you need to know how much volume of solution, right? If you have an IV bag, you have a given volume of that, and the concentration of whatever drug you're being given. You need to know how much volume you need to deliver to that patient, because you need it in units of grams and not necessarily units of concentration. That doesn't necessarily tell you how much you're going to give the patient. The amount you're actually giving them is related to the mass or the moles of that drug that you're trying to deliver to them. Okay. Are any questions on that one? We're going to keep going over examples, but we're not going to focus super heavily on mass to volume percentage, but I just want to give you this so that you guys are exposed to this. Mass to volume, mass to mass, and volume to volume aren't as important for us as something like molarity. But it's also good practice for unit conversions, because when we're looking at these things, we're just looking at, how do the units work out when we want to solve for these. Okay, so here we have a mass to mass concentration, and it's asking how many grams in, what would that compound be named? Potassium chloride, right? This is potassium chloride. How many grams of potassium chloride are in 225 grams of an 8% mass to mass solution? Right, and I'll start off that when you're given, what the hell? When you're given a concentration of mass to mass that's identical to the same way we defined it as mass to volume, except we're looking at mass to mass, so it won't be grams per milliliter. It'll be 8 grams per 100 grams of solution. All right, that's how you can start for this problem. So see if you can figure out how to go about this. Just think about where you're starting from and what you want to find. Starting from 8.0% mass to mass. Zero percent mass to mass, and you want to end with units of what? Grams of what? Grams of potassium chloride, right? That means that the units that we're actually looking at when we make this ratio is grams of potassium chloride to grams of solution, right? These 2 grams represent different amounts of things. Right, so it's the same way when we do our mass-to-mass calculations in mole ratio. Moles or grams of one thing do not correspond directly to moles or grams of another thing. The units of what it is that you're measuring matter. So we're starting from 8.0 grams potassium chloride per 100 grams of solution. So what do we need to multiply this by? Yeah, 225 grams of solution, right? 225 grams of solution, because that's the amount of solution in units of grams that we're looking at. So grams of solution cancels out, and you get 2.25 times 8, 2.25 times 8, you get 18.0 grams of potassium iodide. We can take a look at our values and see if they make sense. We have 8 grams per 100 grams of solution. We have a little over 2 times that amount of solution, so we should have a little over 2 times the amount in the solution, right? And we do. We have more grams of potassium iodide than we do per 100 grams of solution. So at least the value makes sense in that regard. This would be a mass-to-mass calculation. In a volume-to-volume calculation, would be similar, except you're just looking at volume of solute per volume 100 milliliters of solution. In that case, it would be if you're mixing 2 liquids together is how you would determine that. Okay, any questions on this problem? No? All right, so let's go to our more important unit, which is going to be molarity. The moles of solute per liter of solution. It's given by capital letter M is how we denote the unit molarity, and what that means is just moles per liter, right? So it'd be 1 mole, whatever the molarity value is, per 1 liter of your solution. So if we have a solution containing 1.4 moles of acetic acid in 250 milliliters of solution, what would be the molarity of this solution, right? So we're asking, what is the molarity of solution given 1.4 moles of acetic acid in 250 milliliters of solution? All right, so does anyone know what the first step would be here? All right, molarity we know is defined as moles per liter, right? So what do we have to, what would be the first step in solving this problem? Yeah, we have to convert what into what? Yeah, we see that this is given in units of milliliters, and molarity is given in units of liters. Right? Molarity is always given in units of liters. And so we need to convert milliliters to liters. And so how many milliliters are in 1 liter? A 1,000, right? Milli is the prefix for 1,000. So if we have 250 milliliters, what is our conversion factor between these to get to liters? What goes in the numerator and what goes in the denominator? Yep, 1 liter over 1,000 milliliters. And this will give us 0.25 liters. And so if we have 0.25 liters, now how do we find the molarity, right? How do we actually find molarity? What's the second step for this? Right, what is molarity defined as, and what are we given in the problem, right? So we're given the volume, and we're also given what? The number of moles in solution, right? So how do we get molarity from moles and liters? Okay. Yeah, we just plug it into our definition of what molarity is, right? Into molarity, which equals the moles per liter. So we have 1.4 moles of acetic acid per 0.25 liters. We plug in that value. So we get 1.4 divided by 0.25, which is the same thing as multiplying it by 4. And we get 5.6 moles per liter. Those are our units, which is also the same thing as saying 5.6 molarity solution. All right, so the key takeaways from this is that when we're calculating molarity, we have to make sure that our units are working out. Molarity is always given in units of moles per liter, right? So if we're given another unit of volume, we have to convert it to liters. Second thing is that we just then divide the moles by the volume of the solution in liters, and that gives us our concentration. As you can imagine, usually you're not measuring directly the moles of your solute in this case. What are you usually measuring? Right, if I asked you to make a solution of a certain concentration in lab, and I asked you to dissolve an amount into a solution, what would you probably measure instead of moles? If I said put this amount in the solution, what would you probably measure of this amount? Because you're probably not going to measure moles. We don't have any direct way to measure moles, right? Unless you want to count every single atom that's in your substance. If we have a volume and another concentration, we can use milliliters. That's one way to do it. What's another way? The mass, right? If you know the mass, you can use the molar mass to get the number of moles, and then divide that by the volume of the solution. That gives you concentration. If you're mixing two solutions together and you know one concentration, you can take the concentration, multiply it by the volume. That gives you the number of moles, divided by your new total volume of solution. That gives you the new concentration of the mixture. And so we'll have plenty of practice doing that, right? So when we're calculating molarity, we have to make sure the units are working out, and we have to be aware of any other conversions we might need to do. That involves making sure we go from milliliters to liters, for example, or if you're given kiloliters, back to liters, or if you're given grams of a solute, converting that into moles, or concentration of a solution, converting that into moles. All right, any questions on this? All right, so here we have a question asking, what is the molarity of a solution, right? So you're trying to solve for what? What do you want to find? Molarity, right? So we're identifying what is the question asking? We want molarity. Number one is equal to, prepared by dissolving 60 grams of sodium hydroxide, NaOH, in 0.25 liters of solution. All right, so you're given the grams of sodium hydroxide and the volume of the solution. So what do you guys think the first step is going to be? Convert grams to moles, right? Because their concentration is given in units of moles. Convert grams to moles. And then the second step is going to be what? Yeah, just use the formula, the definition of molarity. right? We just plug it in, molarity, which is just defined as M is equal to moles per liter. And thankfully, our volume is already given to us in units of liters, so we don't have to do another conversion. All right, so why don't you guys take 2 minutes to convert 60 grams into moles of sodium hydroxide. Convert grams to moles. What do you have to use here? The molar mass, right? Whenever we're going from mass to moles, we use the molar mass. So we start with 60 grams of sodium hydroxide. And we multiply that or divide it by the molar mass. What was the value of the molar mass of sodium hydroxide? Yeah, what's the molar mass of that molecule, NaOH? 39.99, we'll just say 40.00 is close enough. But yeah, that's correct. 40.00 grams per mole of sodium hydroxide. Grams of sodium hydroxide. All right, so that's how we get the molar mass. So where did you get the molar mass from, Vanessa? The periodic table, right? You just add up the molar mass of every atom that is in that molecule, which is 1 sodium atom, 1 oxygen, and 1 hydrogen. Right? So you want to be very comfortable being able to do that. And so that gives us a conversion factor. So what goes in the denominator and what goes in the numerator? Yep, 1 mole NaOH per 40.0 grams of NaOH. Right? We know it has to be in this order because we want units of moles, and we're starting from units of grams. So we need the units of grams to cancel out. Grams, and when we plug that in, we get 1.5 moles of sodium hydroxide. Another way that you can do this quickhand is if you make your flow chart, right here we know grams to moles. We use the molar mass of sodium hydroxide to go between that. If we look at our arrow, moles is going to be in the numerator and grams is going to be in the denominator. Whatever comes before the arrow goes in the denominator, and whatever comes after the arrow goes in the numerator. Right? So those should always work out that way. Why? Because those are the steps in our unit conversions. So that's why it's important to be able to write that flow chart down. And generally, if you're doing a quiz or an exam and you're plugging in a bunch of numbers, if I see that there is some reasoning to the order of ways you're plugging in numbers, even if you get the answer completely wrong, I'll give you some credit for at least understanding that there is some order to the process. All right, so you get the number of moles, and then what do? Yep, we plug it in our formula, so that means that we have 1.5 moles of NaOH over 0.25 liters. And so 1.5 times 4 is what? 66 molar solution. Moles NaOH per 1 liter, which is the same thing as saying a 6.0 molar solution. Oops. Right, so here it's the exact same as the last problem, except you're not given the moles directly. You're given the grams, which is usually what you'll be doing to make a concentration of a specific value in lab. All right, so this means that just using this, and now you can make solutions of any concentration you want. If you're given the amount of something, you can always make the desired concentration by weighing out the according amount that corresponds to whatever moles you want to find, and then dissolving it in 1 liter of whatever your solvent is going to be. All right, so if I said, make a 0.5 molar solution of sugar in water, you would calculate how many grams of sugar corresponds to 0.5 moles, and then dissolve that in 1 liter of solution. So these are very explicit questions asking for what is the molarity of the solution, but they can be asked in a more practical an application-based way, right? Like make a solution of a specific concentration. That means you have to know how many grams to dissolve in a given amount of solution. All right, so see if you can figure this one out. What is the molarity of a solution that contains 75 grams of potassium nitrate in 350 milliliters of solutions? All right, so I'll let you guys. So what's the first step here? Convert grams of potassium nitrate to moles of potassium nitrate. Why? Because we know the units for molarity has to be moles per liter, and we're given grams and milliliters here, right? So we also need to convert what to what? Yep, we need to convert 350 milliliters to liters of solution. So for the first part, we start with 75 grams of potassium nitrate. What's the molar mass of potassium nitrate? What do you guys get? 101.11 grams potassium nitrate per 1 mole potassium nitrate. So again, calculating the molar mass of a molecule is very important. Should be very comfortable being able to do that. We just use a periodic table, and the molar mass is given to us there. And then how do we use this molar mass? What goes in the numerator and what goes in the denominator? One mole in the numerator, right, because we want to end with units of moles. In the denominator, we have 101.11 grams potassium nitrate. Our units cancel out, grams, grams, and we're left with our answer in moles. And so what do you guys get for that? Should be 742 moles of KNO3. Then we have to convert 350 milliliters into liters. So 350 milliliters. What goes in the numerator and what goes in the denominator to do this conversion? What goes in the denominator? 1,000 milliliters. In the numerator, we get 1 liter. Right, we want units of liters to cancel out. Our conversion is 1,000 milliliters equals 1 liter. Units cancel out, we're left with units of liters, so we get 0.35 liters of solution. And then the last step for this problem is what? Yep, you just plug this into our definition of molarity, which is moles per liter. We have 0.742 moles KNO3 per 0.35 liters. We plug that in, plug it into my calculator. 0.742 divided by 0.35. We get 2.12. Technically, it should only be 1 sig fig or 2 sig figs molarity solution. All right, did everyone get that? Yeah, okay. Are there any questions on if we're given a amount of solute and a volume of solution on how to calculate molarity? All right, so here, familiar with going between grams and moles and also making sure you're using the appropriate volume units. So you can see this can just layer into all of the other unit conversion problems that we've been talking to. Why? Because once you're in units of moles, you can use stoichiometry to go to products of something else or to amount or moles of a compound or element within a compound. All right, so if you mix two solutions where you know a reaction is going to happen, now all of a sudden you know how to go from moles of one reactant to moles of product based off of solution concentrations, not just mixing 2 grams of things together. Okay, but we're not going to do that just yet. Right? That's just a way that we can make our problems harder. We'll realize what I said a little bit ago, whereas if you want to find the amount of solute given a concentration, how would you use a value of molarity to do that, right? So I want to find amount of solute. And in molarity, that amount is given in what units? All right, what are the units of molarity? Moles over liter, right? So the amount of solute is given in units of what? Moles, right? The amount of solute is given in moles, right? It's not given in grams. Moles is the amount, right? It's the amount of solute that we have. So this is given in units of moles. So if we're trying to find the amount of solute for a given concentration of solution, meaning your given molarity in these situations, you're given the molarity of the solution. And you want to find out what is the amount of solute in there. How would you use the value of molarity here? Right? If we have the value of molarity, what would we multiply that by to get units of moles? Right? If we want to get units of moles, our units are moles per liter. Right? What would we multiply the concentration or the molarity of a solution by to get units of moles? By a volume, right? We multiply this by the volume. By volume in liters. All I'm doing is I'm just saying in words that moles solute equals the molarity times the volume. Right, and we see that the units cancel out that way because the molarity times the volume is the moles per liter times the liters of solution, leaves us with units of moles. So we can also do this in another way. We can ask, what is the volume of the solution? In the way that we ask this in a practical application is we say, well, if we want a specific concentration of a solution, right? That's our concentration of the solution. And we're given a specific mass of the solute. What is the amount of solution we need to dissolve it in, or the amount of solvent that we need to dissolve that in? Right, so this one is asking, how do we solve for the volume? How would we use concentration and the moles of solute? How would we get those units to work out? Okay. Yeah, that's exactly right. It would be the molarity divided by, well, so let's try that out first. The unit of concentration is moles per liter, right? So here we get the molarity, the moles cancel out, right? But we're left with what? We're left with 1 over the volume, right? So we did the inverse of what it is the unit we're looking for, right? Because we don't want the inverse of the volume, we want the volume itself. So what do you think we have to do with this relationship here to get the correct relationship? All right, so this gives us the inverse. How do you think we'll use moles and liters? It's almost right. You just flip it around, right? If you just flip this relationship, then you get what you want, right? So if we take the moles of solute and divide that by the concentration, we see we get moles over liters. This is the same thing as moles times liters over mole. These cancel out, and we're just left with units of liters. So all that means is if we want the volume of solution, we take the moles of solute and divide it by the concentration of that solution. And this relationship isn't an exact, formula or equation that you use. This is a way of phrasing a question. If I have a certain amount of solute and I want a specific concentration, right? This is the amount of solute that I have, and this is the concentration that I want. What is the volume of solvent I need to dissolve that in, right? And that's what you'd be solving for here. This one is the opposite. It says, well, I know I'm gonna have a 100 milliliter solution, and I want this specific concentration. How much solute do I need to measure to dissolve and make my desired concentration solution? Those are practical ways of, rephrasing these relationships here. And again, really we're just kind of looking at units and seeing how things match up, right? Units are very important, and we're using solution concentrations as our units now. All right, any questions on these relationships here? I'm doing extra long breaks so people can get some coffee today. So you guys said you didn't do any fun this weekend, but it looks like you guys did. Okay. So here we're given a practical application, right? How many moles of nitric acid are in 325 milliliters of 16 molar nitric acid solution? All right, so we're asking to solve for what? The number of moles, right? This is what we want. We want the moles of nitric acid, HNO3. And we are given what two things? What two things are we given in this problem? We're given the volume, and we're given what? The molarity, the concentration, right? The volume and the concentration of solution. And so how are you going to use these values to then solve for the moles of solution? How do you get the amount of solute given the volume and the concentration? Right, we could even start from our concentration is equal to moles over the volume. How would we rearrange this to solve for the moles? Yeah, we just multiply the volume to both sides. Those cancel out on the right-hand side, and we get the volume times the molarity is equal to the moles. And how would we use that in our problem? We just multiply the values. We get 325 milliliters times 16, and molarity is defined as moles per liter, right? So this would be 16 moles per 1 liter of solution. So will that work? Will we get the right answer if we do that? Why not? We have to convert our volume into liters, right? And so 325 milliliters times what gives us units of liters? What should our ratio be? What goes in the numerator? 1 liter, and then the denominator, 1,000 milliliters. So that gives us 0.325 liters. So now we can rewrite this as 0.325 liters, 16 moles of our solute per 1 liter. Units of liters now cancels out, and we get our answer. And so we get 16 times 0.325. We get 5.2 moles of nitric acid. Right, so you can start directly from the relationship if you want. Volume times the concentration will give us the moles, and make sure that the units work out. Or you can start from our definition of molarity and algebraically solve for that relationship as well. Both are perfectly fine. We just have to make sure that all the units that we're dealing with are matching and canceling out when they need to. So who has an idea how you can make this question one step harder? What could I ask for instead of the moles? If I ask for the grams of nitric acid, right? So if I ask for the grams of nitric acid, what would you have to do with this answer here? Convert it into grams using the molar mass, right? So that'd be one extra step. Taking this value of moles and converting it into mass using the molar mass. All right, any questions on this? Okay. So here we have how many grams of potassium chloride would you need to prepare a 0.25 liters, so you want a target volume, of a 2 molar potassium chloride solution. So now we're asking how many grams of the solvent do we actually need to dissolve in what volume? Yep, a quarter of a liter to actually make the concentration that we want, right? So let's say we're trying to make a target concentration of a solution. This is the question we'd be asking ourselves. And you're asking to solve for what? Grams, right? So this is the amount that we would actually measure out, right? Because it's not easy to measure moles in real life. We measure grams. So why don't you guys take a couple minutes and see if you can figure out how to go about this one. Let's think of it as a two-step process. First, find moles from molarity and the volume. And 2, find grams from moles. So in step 1, the molarity equals the moles per unit volume. So how would I rearrange this to solve for moles? Multiply both sides by the volume, right? We multiply both sides by the volume. What happens to volume on the right-hand side of this equation? They cancel out. And we're left with the volume times the molarity gives us the moles of our solute. If we plug in those values, we get 0.250 liters times 2.00 moles per liter, right? That's the unit of our concentration. That's what molarity is defined as. Do we have to do any conversions here, or does it look okay? It looks okay, right? Because our volume is liters and molarity is given in units of liters. So the liters cancels out, and we're given 0.5 moles of solution of potassium chloride, right? Because this molarity is the moles of potassium chloride in our solution. Molarity is defined as the concentration of our solute in the solution, so that's what we're looking at. The second step is to then convert this into grams, right? And how are you going to go from moles of potassium chloride to grams of potassium chloride? The molar mass, right? And what's the molar mass of potassium chloride? 75 point what? 55 grams per mole. And how'd you get that, Tiffany? Yeah, from the periodic table, right? So potassium was, what was it? Can't see, 39.0 for 0.10, 39.10 grams per mole, plus chlorine, which I think is 35 point something. 35 point what? 0.4 grams per mole. This is the molar mass of potassium, and this is the molar mass of chlorine. That's how we get the molar mass of the molecule. We then use this value to go between grams and mole, because the molar mass is our chemical quantity that allows us to go between grams and moles. So we start with 0.5 moles of potassium chloride, and we put what in the numerator and what in the denominator. What comes next? What goes in the numerator? Yep, 74.55? Okay, just making sure. 75.55 grams KCl per 1 mole KCl, right? That's how we define our molar mass. We see the units of moles of potassium chloride cancel out, and we're left with grams, which is exactly what we're solving for. So if we plug this into our calculator, what do you guys get? 37 point, and then we have 3 sig figs, so we'll just keep it at 37.8 grams of potassium chloride. All right, and what this means is that if I had 2.5 or 0.25 liters of water, and I wanted to make a 2 molar solution, I would need to weigh out 37 grams of potassium chloride and dissolve it in that volume to get the concentration that I want. Right, so if I ask you, make a solution of 2 molar potassium chloride, and you have a 0.25, a quarter liter beaker is the only thing you have available to you. Then you would say, well, my final volume is going to be 0.25 liters. I know my target concentration is 2 molar is what I want. How much potassium chloride do I need to weigh out? This is the exact same thing as what this question is asking, right? I would need to weigh out 37.8 grams of potassium chloride on a scale, dissolve that in my beaker and fill it up to the top, and that would give me my desired concentration. All right, so this is thinking of it as a 2-step process. All right, any questions on this? How do you guys feel about it? Thumbs up, thumbs to the side, thumbs down? Okay. If it helps, you can also think of this as a unit conversion. If you are comfortable with the way it is, you don't have to do a unit conversion. But if we start from 0.25 liters and we're given a concentration of 2 molar solution, a 2 molar solution is basically saying we have 2 moles of potassium iodide per 1 liter of solution. And this is 0.525 liters of solution. Our concentration can be used as a conversion factor where we get 2 moles potassium iodide and over 1 liter and 1 liter per 2 moles of potassium chloride. Sorry, not potassium iodide. 1 liter of solution. SOLN is an abbreviation for solution. And if we want to find the grams of something, we can start from the volume of solution to get the moles of solute, and to go from moles of solute to grams of solute, we can think of this as another conversion step. Right, so if we did this, we would use the concentration to go from volume of solution to moles of solute, and then we'd use the molar mass to go from moles of solute to grams of solute. So that would look like 0.25 liters. Which conversion factor would we use that we wrote above, the left or the right? The left, right, because there's units of moles in the numerator. So we have 2 moles potassium chloride per 1 liter. And then the last one is using the molar mass, which was 75.55 grams per mole. 75.55 grams potassium iodide per 1 mole potassium iodide. All right, so we've set this up like our traditional unit conversion problems. Liters cancels out, moles cancels out, and we're left with grams, which is exactly what we want. And we would get 37.8 grams of potassium iodide. So you don't have to do this in a unit conversion, but if you're more comfortable, this way also works. Sometimes it's just a little harder to see directly formulating or making our conversion pathway, right? Because we have to start from the volume of solution, which is a little bit counterintuitive, or not necessarily intuitive. Not counterintuitive, but it isn't necessarily intuitive. All right, so you can do both of these ways. One, as a two-step process, find the moles, convert that to grams, or a unit conversion going from volume of solution to grams of solute using the concentration as a conversion factor. Okay, so we'll end it there. We'll start lab at about 3:25.